machine learning.
And oh, before I start recording, is it okay if I record?
Yeah,
Matthias?
sure. I still need access to share my screen.
Should be good to go now. Let's try that.
Yeah, it works.
So how are things going with the startup?
Oh, pretty good. It's still super confidential, but yeah, we're planning to have a first demo ready in May. So it's a busy late, but we're still good. I can ping you if you're interested in May.
Yeah, I think before you mentioned like April, May timeframe or something like this.
Yeah, that's true. But yeah, still have time to give some talks. It's not like yeah, but yeah, mostly as an engineer working now instead of a researcher. But still interested in maintaining PyG for a long time, obviously.
Oh, great. I was just kind of, I guess, being a salesman almost of why in my course we'll use PyG as compared to other libraries, and had a couple slides like saying like, here's the competition and pros and cons and things like that.
Yeah, I mean, at one point you have to decide, right?
Well, it looks like some people have joined, so yeah, thanks everyone for attending. So today we have Matthias, who is a fourth-year PhD student at TU Dortmund. He's also a co-founder of kumo.ai, which is looking at leveraging state-of-the-art graph neural networks to kind of make them available to large-scale data. Essentially, his main research interests are in geometric deep learning. He's the creator of PyTorch Geometric, and today he'll talk about some topics related to scalable graph neural networks. Thanks.
Yeah, thank you for the introduction. I'm very happy to be here. So yeah, thanks for the invitation as well. And today I'm talking about auto-scaling graph neural networks. So I will give a brief introduction into graph neural networks and then talk more about like how to scale them up, both like from a theoretical point of view, as well as like regarding implementation and practical use. Yeah, so my name is Matthias Fey. I'm living in Germany, working at TU Dortmund, and currently also building my own startup regarding graph neural networks. And yeah, happy to give that presentation here. Like if you ever feel that there's some question, like please feel free to ask it immediately. I'm always a fan of like some live discussions inside the talk. So to get started, since I'm not sure if everyone is here familiar with graph neural networks, I will give brief introduction first. And like the main motivation is that we want to apply deep learning to other kinds of structures or data besides like images or audio signals and text. And so to overcome the current restriction of deep learning that requires to learn on fixed size structure, we still need some kind of neural network architecture that is much more broadly applicable. So if you think of GNNs, those will require some grids as input, and then like operate in the sliding window fashion. And if you have a sequence like audio signals or text, you can input that into a transformer or a recurrent neural network, but it's like not really clear, like how do we actually process other kinds of data. And as it shows, like there exists numerous data that we can actually make use of and apply machine learning on top of it, like say for recommendation, we have big social networks and we want to do link prediction on them, like recommend new articles, new users, and so on. We can also use it in drug discovery, and the most prominent example here is like learning molecular properties on molecular graphs, where atoms are described as nodes inside our graph, and then we have like bonds between those atoms to describe our edges or relationships between these atoms. We can also like apply them in knowledge graphs, where we like want to infer missing information in an existing knowledge graph or general reasoning in knowledge graphs. And so it's like those are the big three applications, but there obviously exist many, many more, like graph matching, where we want to find the correspondences between different nodes in a graph. So you can think of like having two social networks and you want to find the same user in both of these networks, for example. Another application or various applications exist in computer vision, where we want to like do scene understanding, like giving motion capture data in the form of a skeleton graph, or we can have like scene graphs and we want to learn the relations between objects in our scene and so on. And the last major application would be in combinatorial optimization, where we use it to replace some simple heuristics. So how do we actually learn on such kind of graph structured data? And the general class of neural networks that got developed here are known as graph neural networks. And I always see them as some kind of generalization of convolutional neural networks. But of course, there exist like endless possibilities to describe them. And the most prominent approach for defining graph neural networks is based on following a differential message passing scheme. And that basically just means that we get the central node representation in for a given node, that is here denoted as HV in layer L. And we also get the representations in of all the neighbors of that given node, which is here given in that multi-set of neighboring node features. And we take that into our neural network layer, which is here given as F, parameterized by some parameters, and we get a new representation out for the given node. And so that basic blueprint here can be decomposed into three major components, which basically makes that a message passing scheme. That is, for each neighbor of that given node, we compute a message, and that message may depend on the central node itself, but it certainly needs to depend on the features of the given neighbor. And then we can send all these messages to the central node, and we somehow need to aggregate them together to get a unified representation of that neighborhood back. And that is here denoted by that aggregate function that just like tries to aggregate all the features of all the neighbors together. And at best, that is like done in a permutation-wise fashion, since we cannot assume any ordering of the given neighbors. Like typical examples for that would be sum aggregation, max aggregation, mean aggregation, and so on. And finally, we can use that aggregated result and update the central node representation based on it. And so we can have another function update, which takes in the central node representation and the aggregated result and computes a new representation for that given node. And so these are the main three steps of that differential message passing scheme. Importantly, like these functions are trainable and differentiable, so we can use them as building blocks in our neural network architecture. And even more importantly is that all these functions are shared across all nodes, which means that like we make use of the concepts of shared weights. And we can also apply our GNN or GNN layers on unseen nodes as well, which makes them applicable both in a transactive and inductive scenario. And so if we stack these message passing operators or these building blocks, we will actually get a graph neural network if we combine that by nonlinearity functions. And so if we stack like these layers L times, we actually aggregate the L-hop neighborhood around each node. And so you can think of that as like in the first layer, you will aggregate all the direct neighbors of a given node. And then that representation will actually represent the one-hop neighborhood of that node. And if you do that a second time, you again aggregate the features of the direct neighbors, but those will now contain already the one-hop neighborhood information around their nodes. And so it actually already corresponds to a two-hop neighborhood information. And so we can use these node embeddings, these local node embeddings we get for each node for various different tasks. And there exist like these three major tasks, which are known as node classification, where we want to do prediction based on the given node embedding. And that basically just means that we can input our node embedding into an MLP, which acts as our classifier, and then train our GNN and classifier jointly together using stochastic gradient descent. We can also do graph classification. In that scenario, we would need to aggregate or read out all the node embeddings into a unified graph level representation, in which case we can sum all node features up or average them together, whatever, and then apply a classifier on top of these graph level representation to make predictions on an entire graph. And the second task would be the link prediction task, where we want to predict some properties or some existence of links based on pairs of node embeddings. And now we can maybe add the concatenated input of node feature of node V and node W together and input that into a final classifier. Any questions so far? Sounds good. Next, I want to briefly talk about expressive graph neural networks because we need it later on in our talk about scalability. And so there exists various works that tries to understand how expressive these GNNs actually are. And so it's obvious that these GNNs, like to some extent, like capture feature information in this local neighborhood because like they aggregate from neighboring nodes and so on and compute new node features. But it's actually like it is worth questioning, like, how do they actually capture graph structure? And so ideally, a GNN maps isomorphic graphs to the same representation, in which case isomorphic means that the two graphs are topological identical, which means that they only differ permutation-wise. And so two graphs here would clearly be non-isomorphic because they do not even share the same number of nodes. But more importantly, a GNN can also map non-isomorphic graphs to different representations. And that means that ideally, a GNN would have to solve that like challenging graph isomorphism problem where we like detect if two graphs are non-isomorphic. And even better would be if the GNN can map two non-isomorphic graphs to different representations, but the distance in the embedding space also like acts as a way to describe how far the two graphs actually differ, like if they only differ in one edge or two, and so on. And so one can actually show that as long as the GNN is permutation invariant, it will map isomorphic graphs to the same representation. And that is like pretty obvious to see, especially like since all GNNs are permutation invariant by design, as long as they make use of a permutation invariant aggregation operator like mean or max or sum. It's more interesting if we think about like how powerful these GNNs actually are in distinguishing non-isomorphic graphs. And there you can actually show that the power of GNNs is highly related to the Weisweiler-Lehmann graph isomorphism heuristic. And it's actually equivalent to that heuristic if the aggregation scheme that we are using is injective. That means that different multisets of features of neighbors get always mapped to different representations in the output space. And so the Weisweiler-Lehmann graph isomorphism heuristic is pretty powerful, and it can nearly detect like for almost any graph if they are non-isomorphic, but clearly it's a heuristic. There exists some failure cases, but it's usually not that dramatic in practice or in real world applications. And so just to give you a sense of what that actually means, that an aggregation scheme needs to be injective, here's some simple examples how to show that where some aggregation scheme fails. Like if you look at figure A here, you can see that one has either two neighbors or three neighbors, but all the neighbors have the same set of features, which is here denoted by the color blue. And it's clearly like if you just mean or average all these neighbors together or take the maximum here, then the aggregation scheme is clearly non-injective, like it's maps both representations here to the same destination. The same holds true for figure B here, where we use max aggregation. And that here shows that max aggregation clearly fails to distinguish like how many neighbors are actually present in the neighborhood. And a figure C is another example where mean and max fails as long as each feature set differs is same in the cardinality. But clearly, for some aggregation, all these different use cases here can be distinguished. And so as a general rule of thumb, it says that as long as we use some aggregation in our GNN, we can become injective. There exists some additional properties that needs to be fulfilled, but in general, that's the minimum requirement that we need to have. Although it also have been shown that we can get true injective representations using other forms of GNNs, for example, like using multiple aggregations and so on. Cool. Next, I want to talk about scalable graph neural networks, and this will mostly cover my ICML paper about GNNAutoScale, where we want to like combine expressive and scalability into a unified framework. And so what does scalability regarding graph neural networks actually mean? It means that we want to learn on really giant graphs. And with giant graphs, I do not mean here a set or a large set of small graphs, like for example, learning on a data set or a large data set of molecular graphs, but I really mean like we have one single giant graph, like a social network or whatever, and we now want to learn on that social network. And so why is it hard? Because usually we need to apply some mini batch techniques here in order to efficiently learn on that. Like imagine that you have a giant single graph. It's obvious that that graph will not fit into GPU memory because like they tend to be like terabyte of size. And so we need some kind of mini batching technique here to make that really learnable in a deep learning fashion. And if we naively apply mini batch techniques here, then we will get to know about the neighbor explosion problem, which means that there will be an exponentially increasing dependency of nodes over layers. And so to illustrate that, you can look at the figure at the bottom. And the goal here is that we want to learn a representation for the orange node. So just for that single node here in that graph. And if we do so, we will see that in the first layer, we will need the information of the direct neighbors of that node. And in the second GNN layer, we will actually need the information of the neighbors of these neighbors as well. And so in theory, depending on your graph and how it is structured, you actually have an exponentially increasing dependency here of neighbors with respect to your number of layers. And so you can see that even after 3 layers here, we will actually need the whole graph in that illustration here to compute the representation of the single node. And so there exists some ideas on how to make that scalable. The most common approaches here work by sampling edges. And so there exists various techniques here, and they are categorized into 3 major parts. One is node-wise sampling strategies, the other is layer-wise sampling strategies, and the third one would be subgraph-wise sampling strategies. And so for node-wise sampling strategies, the idea here is that we only sample a fixed amount of neighbors per node and per layer. And so here in that figure, we only allow that each node and each layer samples a single neighbor. So in that example here, V1 would only sample its neighbor V4, and V4 will again sample V6, and V1 will sample again V3, and so on and so on. But we still see that our computation graph here on the right gets wider the deeper our GNN gets. And so to avoid that, there exists the idea of subgraph-wise sampling, where the idea is that we only sample a fixed subgraph, like say the 4 orange nodes here, given in that example, and we calculate the induced subgraph of these nodes. That what basically means that we throw away all other nodes and edges not part of that subgraph, and we only apply our GNN on top of that small subgraph here. And so what you see here is that our computation graph stays the same even if we go deeper in our GNN. Like we can go dramatically deep, but the computation graph is still local or fixed in size. And so while these approaches usually work pretty well in practice, they still have some disadvantages. So what I said, like neighbor explosion still takes place in node-wise sampling strategies, which means that we are just like reducing the factor by which we increase exponentially, but the exponential factor is still in there. So that's pretty bad. And that the general rule of thumb, like you cannot go deeper on S3 layers in a node-wise sampling approach. But subgraph-wise sampling obviously has limitation as well, because like we are restricted to learning from that shallow subgraph that we actually sampled. Like there's no way for us to get any information outside or from outside node, outside of this subgraph, right? And if we like think about like learning from information far away in your graph, like subgraph-wise sampling approaches obviously will just fail here. And what both approaches have in common is that their inference still needs to perform on the full graph, which means that we still want to apply inference on the full data. And since the sampling of edges can be usually framed as some kind of dropout of nodes and edges, it's obvious that one does not apply dropout during inference because like you still want to receive all the signal present in your data. But the most important problem is that just by the act of sampling edges, a GNN will actually fail to learn about structural graph properties. And so you can just illustrate that pretty quickly if you think about like learning specific motifs in your graph, like triangles or circles and so on. And then your GNN will just fail if you do not sample all the edges that are present for making that or detecting these patterns in your graph. And so just by the act of like missing information, our GNN will get a reduced expressivity, right? Independent on how expressive your GNN is in the first place. If the data is not present anymore, it cannot learn it. And so what we ask here is how we can actually learn structural graph properties while still being scalable, like while still being able to apply GNNs to massive graphs. And what we came up with is our GNNAutoScale framework, which leverages the idea of historical embeddings, which was presented sometimes earlier in a GNN scenario in a different context. And the idea here is that we use the historical embeddings to approximate the missing out of mini batch information for each layer. So if we look at the GNN formula presented earlier, we can actually see that we can decompose the multiset of features of neighbors into two parts. So one part describes the multiset of neighbors that is well part of our mini batch. We call these the in mini batch nodes. And the second multiset denotes the neighbors that are not part of our mini batch. And so if you think of subgraph-Wise sampling strategies, then the idea here is to just throw away that second multiset, and we just like restrict learning on that first multiset. And here the idea is that we actually approximate that second multiset using historical embeddings. And what does historical embeddings actually mean? It means that we represent the node embeddings here, or we approximate these node embeddings here by the information we acquired in previous training iterations. So it means that whenever we compute a new node representation, we save it in an offline storage, detach it from the computation graph, and then we can reuse it later on whenever we need that information again. So if we look at the general computation flow here, we will see that we have two operations that are crucial here. The one is that we need to pull the most recent information from the histories from out of mini batch nodes. And we denote that here by the blue arrows. And the second operation is that we need to push newly estimated embeddings of in mini batch nodes to the histories in order to ensure that our history storage is always up to date. And the assumption here is that as long as we keep refreshing our history frequently and our model parameters of our GNN do not change too much, then the history embeddings will denote a good approximation of the correct embeddings. And so to illustrate that here, we will now have like these orange nodes in our graph, which denotes the nodes in our mini batch. And then we additionally have that information about these direct neighbors of this mini batch, which are not part of our mini batch itself. We denote that here as the blue nodes. And if we look at the computation graph, we see that the computation graph still is fixed in its width, but And that means we can stack it as deep as we want, and we do not get any memory increase with respect to the input node size. But importantly, we have these frequent accesses to the history. So whenever we need information from the blue nodes, we pull them in from the history. And whenever we compute new representations for the orange nodes, we push them to the history again. And importantly, like these histories are stored on CPU and do not pollute any GPU memory. And so that has cool advantages because like our computation graph is fixed in size and only requires like having access to local information, which is pretty cool. It actually trains over all data, like no edge is really dropped during training and during inference, which is also pretty cool. And at best, we can also have a constant inference time since we can directly make use of the embedding stored in the latest history to make predictions for a given training, test, or validation split. And it is also really simple to implement because like our graph structure stays the same across different layers, but I will talk more about that later on. Okay, so that approach seems pretty cool at first glance, but if you actually implement that, you will see that it still needs some fine tuning to get it working. But importantly, like the cool thing here, or the thing you need to take home is that this approach makes really use of all available neighborhood information, and so we can really like prove some cool things with that. And one thing we can prove is that the approximation error on the output representations is actually bounded by three major components. One is the stallness of histories, and that means that we need to ensure that our histories get updated frequently. The second is the Lipschitz continuity of GNN layers, which basically ensures that if we approximate the input, we only require that the output, or better saying, like if the input varies by a small factor, then that means that the output also only varies by a small factor. And the third thing is that the number of layers also denotes the approximation error of our output representation, and that is basically because like the errors made in the first layers will immediately get propagated to later layers as well. And so that is a cool result at first, but it has its disadvantages, especially in the number of layers. But you can still show that with this scheme, you do not lose any expressivity in GNN design. That is like, if you have a GNN that is as expressive as it can be, it will not lose any power when applying it to large-scale graphs using this particular GNNAutoScale framework. And that is like a cool result, which does not apply to other scalability techniques. And so, as I said, like if you apply that scheme, then you will see that that it's not performing that well. Like it's performing well for 2-layer GNNs or 3-layer GNNs, but if you really want to stress that out and want to apply it to like the 64-layer GCNs or really expressive Gnn layer, Gnn isomorphic networks, then that just fails. And so we actually see that the effects of histories here are well noticeable for these kind of GNN architectures. And that mostly depends on like the number of layers here, which results in less, in the loss of performance for the deep GNN and the Lipschitz continuity for the expressive GNN. And so luckily, we can easily try to tighten the error boundary for deep-end expressive GNNs. And as I'm pretty sure there exists like endless possibility ways to achieve that. In our work, we did that by reducing the history accesses in the first place. And we do that by trying to minimize the interconnectivity between mini batches. And we do that by partitioning the graph in the preprocessing step. And the first approach, the second approach is that we try to regularize the local Lipschitz continuity of the GNN layers. That is like small variations should only have small effects for the given input examples, but importantly, we do not enforce a global Lipschitz continuity here. And if you apply these techniques, you actually see that we can like resemble full batch performance here with ease, even for deep or expressive GNNs. And so one thing I also want to talk about is how we can actually make that approach scalable and efficient. And if you naively implement that scheme, you will see that these frequent data transfers to and from the GPU that occur due to our history access can actually cause a major I/O bottleneck. And so after each GNN layer executes, we need to push the information that it has computed to the history. So that involves like memory transfer and a push to the history. But we also need to pull the new information for the next layer. And that again, like involves an index select on the histories that we want to select. And then we need to move that data to the GPU as well. And so how do we can overcome that? And the idea is pretty simple, that we like make use like of non-blocking device transfers. And so how does it actually work? The idea is that we can asynchronously copy the histories from out of mini batch nodes to a pinned memory CPU buffer. And within that pinned memory CPU buffer, we can actually make use of asynchronous memory device transfer to the GPU, which is not possible otherwise. And then we only need to synchronize the individual CUDA stream before we actually access the GPU data for the given GNN layer. And if you visualize that in a small figure, you can see like in the sub figure A that a normal full batch GNN just pushes all data to the device here, which is indicated by that H2D naming, which stands for host to device, and then just run like the kernel iteratively on the data. If you apply our serial mini batch execution, like you do not worry about how to make that fast. You first would push the data to the GPU as well. And then you can actually start the first GNN layer and already on the GPU and asynchronously pull the information for the second layer into a CPU buffer, but then you would have to wait for both memory device transfers to be completed. The first one would be the transfer to the CPU memory buffer, to the CPU history. And the second would be that you pull the histories to the GPU again. And so you can actually see that like the kernel always needs to wait for these memory transfers to complete. If you do that in a concurrent fashion, you can see that the memory device transfers actually can work in parallel when they work on pinned memory buffers. And the actual kernel ideally never runs idle as long as the device transfer is faster than the actual GNN execution. And so to evaluate that, we first show that our GNNAutoScale framework is both fast and memory efficient. And we can actually see that it is orders of magnitude faster and consumes orders of magnitude less memory than any node-wise sampling approach. And we compare here with the fastest one that is proposed in literature, and it's still like super fast because like we do not have these exponential increase in neighborhoods and nodes. The second experiment involves about like how well our GPU memory consumption actually relates to the amount of neighborhood information that we use. And we can clearly see that our full batch training would, in theory, make use of all the available data because like no edges are actually dropped during computation, but we get we get a huge GPU memory consumption here. Like training on a 2 million nodes graph would result in like needing 30 gigabytes or 40 gigabytes of GPU memory, which most people don't have, I assume. You can actually make that way more efficient using scalability techniques, of course, like using GraphSage or cluster GCN can heavily reduce the GPU memory size that you need, but on the same side, you actually throw away like 80% or 90% of the data actually present in your graph. And so GAS has that nice attribute or nice advantage here that we can still easily control our GPU memory size while always making use of full neighborhood information. We also see that our concurrent memory access pattern has no runtime overhead, and we can separate the runtime overhead here by the computational overhead, which is involved by just having these additional neighbors that we need to aggregate, and the I/O overhead that is induced by the history accesses. And if you can see that the concurrent access here is nearly equivalent to only the computational overhead of having more edges to aggregate. And that means that our I/O overhead is like nearly non-present. And the last one is obviously that we can easily apply that to large-scale graphs. And importantly, we can do so with any GNN backbone and maintain its expressive power. And that means that we can stack deep or expressive GNNs, and we can actually get a boost in performance on large-scale learning tasks as well. And so we can see here GCN2 and PNA, which are far more sophisticated GNNs, actually heavily outperform the GCN variant using our GNNAutoScale framework. I quickly want to talk about, before time is running out, on the implementation aspect. And obviously, since I'm the maintainer of PyTorch Geometric, we also implemented our GNNAutoScale framework with it. And so just to give a quick introduction into PyG, if you do not know about it yet, it is a PyTorch library to perform deep learning on graphs, point clouds, and manifolds. Its goal is to like simplify implementing GNNs and working with them. It tries to bundle state-of-the-art GNN architectures and training procedures. It tries to be as fast as it can on highly sparse data of varying size. And our recent goal is to make it both usable for academia and industry, in that sense that it should be flexible, so academia is not limited by its scope and functionality, but it also should be comprehensive and easy to use, so that industry can easily make use of recent advancements of research. And the idea here is that we like simply frame PyG as PyTorch on the rocks. So instead of like restricting ourselves to learning on images using convolutional operators, we can easily swap them out with GNN layer implementations. And the only change in implementation really is a change of input arguments, where we now require both node feature matrix and some kind of edge index or graph structure information that gets inputted into the GNN layers. and those GNN layers then compute new node representations out of that. So for GNNAutoScale, we also saw a bit about its implementation, and the general goal here was that the implementation of GNN should be agnostic to its scalability technique. And so ideally, we can write GNNs in full batch mode and then let PyG just figure out the rest on how to scale it up. We're still not there yet, but we're trying our best to do so. And then our GNNAutoScale framework provides the necessary theoretical guarantees to provide the equivalence of expressive power. And so importantly, this is not trivially achieved by alternative scalability techniques, since these techniques may require that the graph structure varies across layers, and now you need to input like different graph structures for different GNN layers, and that is like totally different in how you actually write full batch GNNs. And so the goal here in our GNNAutoScale implementation is to make that far more easier to write. And we fully open sourced our solution in a separate GitHub repository on top of PyG. And the goal here is, or the only changes that we need to make is that we now need to inherit from a specific scalable GNN base class. And then we, in the constructor of the base class, we actually pass the num nodes, hidden channels, and num layer attributes to the base class, which takes care of creating the histories and buffers and so on. And then in the GNN execution phase, we just need this push and pull command between two intermediate GNN layers, which take care of like pulling and pushing the history to and from the CPU. And ideally, we can even make that more future-proof by making this conversion of a GNN automatically. And that can be done by the torch.fx interface, which is an interface to modify the computation graph of a given neural network. We have plans to integrate it, but just wanted to mention it here because it is a pretty cool interface and might be useful for your research as well. And so to conclude, GNNAutoScale provably maintains the properties and power of the original GNN. We tried our best to make it as fast and memory as efficient as we can. And importantly, it still makes use of all available neighborhood information. It easily resembles full batch performance, even for deep and expressive GNNs, and it can actually autoscale any GNN backbone model to large scale graphs. And yeah, if you want to try it out, like please check out our GitHub repository. And so for future plans, we have plans to add some multi-GPU training in. So currently it just works in single GPU mode, which means that we need to share like history access across multiple GPUs. But that shouldn't be too hard to add because like there's no overlap in writing or reading from the history. We also have plans to distribute GNNAutoScale, which means that we also need to distribute historical embeddings. And you can think about either doing that per layer or per partition. And importantly, if you store the additional one-hop subgraph of batches inside the same machine, there's like no communication costs in the graph structure across different machines, which is pretty cool. We also think about like adding support for other storage formats of histories. Like currently we're holding everything into CPU memory, and that obviously works well if you're equipped with a good machine with enough RAM, but it certainly has its downside if you think about like terabytes of data. And you can also store that in databases or making use of memory mapped IO and so on. We have plans to play around with that as well. And lastly, we want to add like heterogeneous graph support on top of that. And that means that we need to support our newly released heterodata object inside PyG in GNNAutoScale as well. And so, yeah, that concludes my talk. And I'm seeing that I'm right in time, and I'm happy to take any questions. Thank you.
Great. Yeah. Thank you. I guess I'll probably save any questions I have until perhaps some others. So if you have questions, feel free to unmute yourself and go ahead and ask.
Hi, Matthias. Thank you for a great talk. And I'm also an active user of the PyG, and I really like it. And also this work, yeah. So it's really amazing to see like how you can save both the memory and the time for like large graphs. So I have a question for the subgraph. So is there like any considerations for the choice of the subgraph? So, and would that topology of the subgraph affects its performance?
Yeah, that's a good question. Like I mentioned that we do that pre-partitioning on the subgraphs in order to like reduce the number of out of mini batch nodes, right? And that comes in handy when you really want to stress out the maximum during training, but it isn't required to do so. Like the implementation works fine without that step or with it, but it certainly helps in runtime, but isn't required to achieve good model performance.
Gotcha. Thank you.
Hi, Matthias. Regarding that question, I also have follow-up questions. So yeah, if we use like pre-cluster to select our mini batches, will it be some biases that for some nodes we always use for some nodes there will always be some nodes that they use their historical embeddings. Will it be possible that like during some training epochs we can maybe change how we cluster the graphs so that we can mitigate this bias?
That's a good point, which I haven't really implemented yet. I'm pretty sure you're right that we can limit some kind of bias here. It's similar to the bias that is introduced by cluster GCN, but not so present actually. But yeah, it's a good point. In my opinion, it might not be worth it because like you actually don't want to do that pre-partitioning too often because that limits just your training runtime, right? It's a pretty expensive operation that you hopefully only do once. And we also do this stochastic sampling of mini batches already, similar to cluster GCN, where we sample more mini batches and then group them together.
Okay, thank you. Also, I'm the user of this PyTorch Geometric. It helps me a lot for my research. I have two like quick questions about this. I always have these questions for this PyTorch Geometric. So when I look at the source codes for implement like the GNN layer, like the first we use the linear layer, and second we use the scatter to propagate the information. So when I check the code, like it seems like when we implement the linear layer, the bias term is always there will be a choice that we can add our bias term after the feature propagation. So first a linear layer and then propagation and then add that bias term. Is there any specific reasons for such types of the design?
Yeah, I might be mistaken, but it makes sense to me because like you only want to apply the bias once, right? If you apply the bias before actually gathering and scattering, you will add that term in for each neighbor that you actually add a message to, right? And so your bias now becomes like dependent on how many neighbors are actually present in your data.
Okay, gotcha. Yeah.
So I thought it makes more sense like that, but never tested any performance difference, to be honest.
I think I have one experience. I think your intuition here is quite right. The performance a little bit increases, I think. Yeah.
Okay, great.
Another quick question is about that scatter function. So I also noticed that in the literature, there's another version of implement this propagation using the torch sparse multiplication. So is these two methods kind of similar from the bottom, or there are some differences in terms of the time complexity or space complexity?
Yeah, right. Like if if you can utilize sparse matrix multiplication and the general rule of thumb, you should do that, because like you're saving a lot of GPU memory that way, because you do not need to materialize that edge level representation that you obtain using scatter and gather. But obviously it doesn't work for any GNN layer. It works for the classic or traditional ones, GCN, GraphSage, and so on, which just like applies linear transformation and then just does average across the neighborhoods. But it does not work if you actually combine or have more sophisticated message implementations, in which may involve like edge features or central node representations and so on. And then you will need to materialize the edge level tensor. And so in general, like it is always clever to do it for like certain GNNs, but it may not be possible for others.
Okay, gotcha. Yeah, thank you.
Yeah, welcome.
So I have a quick question. Thank you for the very nice talk, Matthias. Regarding the staleness of the historical data that you're essentially putting on the CPU. So how does it scale when I have a very large graph? Shouldn't I expect the information to be more stale more often than not? And is there a way to like essentially incorporate the staleness into our calculations? If something is very stale, like we don't rely on its information as much. If it's more recent, you should like.
I see you have good follow-up ideas, which I did not explore, but yeah, please feel free to try it out. And obviously, that might be a good choice, like to like additionally store when was the last time we actually update a history and then reweight it, right? So that sounds pretty clever to me. I haven't tested it, but obviously, like there might be some limitations if we actually want to apply that to terabytes of data. And the current workaround we have is like that we require like that we compute fresh histories more frequently on a step size rather than on an epoch size. If that makes sense. But yeah, it's an interesting further research topic indeed.
Thank you.
Yeah, I guess I can jump in now. So the one question I had towards the end, you were talking about the future plans for the distributed learning. And I was wondering that as compared to maybe having some large graph and then applying distributed learning techniques, that if this is maybe coming from some like large organization that already has their data sharded across many servers, or potentially could there be any concerns of how to handle privacy in this type of thing? If you have this distributed setting and the graph might span across even different corporations, for example, and have you thought about any ways that these kind of scalability methods might kind of then link with some privacy concerns in this distributed setting?
To be honest, I haven't thought about it that much since I'm just working on benchmark data sets. But that would be true for any scalability technique, right? That we want to distribute. It's not related to GNNAutoScale, right? Mm-hmm. And so I think if there exists some privacy concerns, like you should be able to select which machine should communicate with which other machine, right? Or just using its own data if there are any concerns. But yeah, interesting topic, but to be honest, I haven't thought about much yet.
Okay, yeah, I guess I was just thinking that potentially in the graph structure itself as well, rather than just from machine to machine, if there could be connections where certain types of propagation should or shouldn't happen, and to what extent. But yeah, just something that came to mind when thinking of distributed training here.
Yeah, I think in most cases, like you apply distributed training to a single source of data. Like you first collect the data and then distribute it for machine learning, right? So your approach would be more related to like having the raw data distributed and then using that machine for machine learning as well, right?
Could be, yeah.
Yeah, interesting. But yeah.
All right. Any other questions that people had? Well, it looks like, yeah, perfect timing with the presentations and the questions. So thank you again. It was really great. Yeah, looking forward to see your future work.
Yeah, thanks for the invitation, and yeah, wish you all good luck in your research.
See you.
Bye-bye.
Cool. I guess still haven't found someone for the next week. I just heard back from 2 people saying that it's kind of too soon.
Right.
But yeah, I'll try to reach out to some others as well.
Yeah, I mean, let's see. I sent one email out. Let's see. I think it's a short notice, right? We are all busy, so like it's very hard to catch up, honestly. But I think that the idea that we had to make an Excel sheet so everything is clear, who is assigned to what. I think we have something like that, but it's not just up to date. So I need to keep that up to date. And if we don't have the speakers, I think like we can do it ourselves too. Like I'm working on one presentation for like to give a talk in upcoming weeks. So I think that I will be able to do one, but at the same time, we don't want to dominate it with all internal talks. Like this is a really good idea to bring other folks in. So we have one for the end of April, and then we are missing the 2 in between, right? Right now. Okay. How many are still? How many invitations are still out?
2. I think when I was messaging them, I kind of just said, you know, generally invited for any time, but preference on these 2 weeks in April. Just then kind of, you know, if more people do reply back, we can just schedule them out into the summer. Where, yeah, maybe we can try to start doing that, yeah, to kind of get the summer filled up so that at that time, yeah, we can kind of break away of this, like, yeah, quickly catching up type of thing.
Right. Yeah. Yeah. Let's see. I think like Matthias' talk was really good. Thank you for inviting him. I think he's a PhD student, but his talk was better than a lot of like folks that we have had. So his talk was really good. I really enjoyed it. Yeah.
Well,
thank you. Cool.
Guess see you at least maybe, if not before Friday morning.
Yeah. Yes, 8:30. Yes, I remember. Are we on Zoom? That's on Zoom, right?
I think so. I think many of the people weren't so interested in an in-person meeting, so just a compromise of Zoom.
Right. But, yeah, and are you on the size carrier workshop that's going on, right?
Yeah, I'm gonna jump back to that now.
Me too. Okay, so see you. Bye.